Okay, so let's get started. Uh, so last class we talked about many important things. In particular, one of the key things that we did was define Turing machines. Okay, and as I said at the beginning, definitions are one of the most important things that we will learn in this class, and in that context, at least, Turing machines is probably right up there. Okay, very simple definition, very simple extension of DFS, and we're going to investigate what powers it gives us. Okay, and then we define what it means to be computable by Turing machines. And we saw our first example, which was majority is computable by Turing machines. Okay. All right. Now, so our goal today is first, I want to do some more, one more example of a Turing machine. Okay, another example of a Turing machine. And, I'll also show a demo, but usually programming a Turing machine or kind of writing it out explicitly will be tedious. But we can start with a high level picture, some sort of medium level of abstraction, and then kind of understand how the Turing machine works from there. Right, and then we'll do some greatest hits really of computer science. One is Turing machines as a programming language. What it buys us, what we can do, and so on. Okay. All right. And in terms of announcements, okay, there's a couple of ones which are important. One, homework 3 is up. Homework 3 or 4? 3, yeah. The website on Gradescope. Okay, and there's also a mid-course feedback survey. This went up on Monday, so just tell us, give us any information that you want to convey about how the course is going, about the discussion sections, or any specific topics or things that you would like to cover. If we can accommodate it, we will try our best to do it. Okay, so if there's any concrete feedback, any changes that you would like to see, we'll try our best to accommodate it. And one of the questions there is the last 3 to 4 lectures. I usually leave it up to students as a whole to pick the topic that you want. And the 3 topics are, one is Kleen's recursion theorem. This is kind of very classical computer science computing stuff, and is a very powerful idea in programming languages and so on. Okay, if you know what that is, you can look it up a little bit before you vote. The other option is Gödel's incompleteness theorem. It's really, it was a big deal in logic, but it's really a question about computability. Okay, so Gödel's incompleteness theorem usually stated as saying, okay, you cannot prove every true mathematical statement, whatever that means. Okay, there is a way to make it formal, and you can only do so really in the context of Turing machines and computability and what we are discussing in this class. The third one is quantum computing. By computing, I just mean, just as we've been doing for most of the class so far, we will be able to define what a quantum computer is. Okay. For other models, we not only defined a model, but also studied its properties. But here, even just getting to the model is kind of tricky, and that's where we'll stop, if you pick that. Okay. So you have an option to vote for one of these three things. We can only cover one, unfortunately. It takes 3 to 4 lectures. And whichever gets the most percentage, that's what we will do. Okay. Any questions? Make sure you fill out the feedback form. Yeah? The last few years, the last topic, quantum computing, has been winning hands down. 1 year I taught clean recursion, 1 year, a couple of years Gödel's incompleteness, but at least the last few years, quantum has been winning. Okay, no, it's good. But for all of these things, we have covered the basics, so it's about exploring additional topic. Okay. All right. And okay, so with that out of the way, let's now go back to Turing machines, right? Oop. And I'm not going to do everything that we wrote down last time, but so this was our idea for majority, right? As I said, it's a very simple function when we think of modern programming languages, right? You can do it in Python just by simple counting or for loop, or even a single call if you want, right? Inline programming, okay? But in this level of detail on a programming language like Turing machines, it can be so messy, okay? Or it's seemingly very messy and tedious, right? As I said, it's a very low-level code. If you know assembly language, it's even lower than that. Okay, Turing machine is even lower. So you have to specify the table, what are the transitions, and so on. Okay. And if you do all of these things, you will exactly compute the majority function. Any questions about this, what we covered last time, and how we can compute majority using a Turing machine? Okay. All right, if there are no questions, let's do one more example to kind of get a sense of thinking like a Turing machine, right? So as I said, thinking like a Turing machine means it's very similar to DFAs. A DFA only cared about what state it is in, what bit it is reading, right? And then jump to a state. Turing machine also has this very local property. It only cares about, or you're only allowed to use what state you're in. And remember, even if you're processing an input which is 1 billion characters long, your number of states is fixed. You're still only going to have like 10 states, maybe 20 states and so on. Okay, the number of states is fixed, right? So Turing machine can only use information about what state your machine is in and what symbol you're currently reading under the head. Right? So in that sense, it's very similar to DFA. And then you have 2 extra properties. That's it. You jump to a state. You can write where you are and move left or right. So it's still very, very local. And the description is decoupled from the input completely. Okay? So keep that idea in mind. Okay, so let's do one more example. I think it's a simple example. Once again, for any programming language that you can think of. If you want to do this using a Turing machine, you have to do something, it's going to be a little bit tedious, but it's fine. Okay, we'll do it once or twice. So palindrome is a function. I'm just going to call it P of x is 1 if x reads the same front to back, right? And 0 else. Okay. So for example, 101, 0110, these are, P of this equals 1. Okay. And my claim is that palindrome can be computed by a Turing machine, right? It's not too hard to show that palindrome is not, what happened? Palindrome is not computable by a DFA. Okay, you can use pumping lemma or you can use MNT to prove that it is not regular function. But nevertheless, we are saying it can be computed by a Turing machine, right? So let's think about that. So I'll state the notation and everything else, and then you come up with the algorithm. For any Turing machine, you are going to assume that the input is loaded onto the tape, right? So you have this, let's say 0, 1, 0, 1, 1, something like this. Okay, this is my input maybe. And then you have a bunch of empty cells. Okay, so your tape comes loaded with the input x, and we're trying to check if x is a palindrome or not. All right. Now, how can I compute this using a Turing machine? Any suggestions, ideas? Yeah. Okay. Yeah. So I think that works. So let me write down what was suggested. So as I said, the idea behind Turing machines, in the restriction that they have, which should really be a severe restriction, is that they can only read pretty much one cell at a time. They can only read one cell at a time. They can only write one cell at a time. They can only move one step at a time, right? It's very, very restricted setup. But nevertheless, we can do some stuff here, right? So the suggestion was, my tape starts off from the leftmost point. For example, I'm here. Now you read the first bit. And you try and go to the end and check if the first bit matches the end, right? But how can I check if the first bit matches the end? Because I cannot access the first bit when I go to the end. So how can I possibly do that or implement that? How can I remember what I read while I go ahead to the end? Any sessions? Yeah? Exactly. We're going to remember it in a state. And the reason we can do that is because it's only two options, 0 or 1. So that only adds like 1 or 2 states. So we're fine. Right? So read the first bit. Remember the bit in a state. Okay? And before going on, I'm going to mark this bit as seen so that I don't get confused again. Okay, I've already seen the 0, so I'm going to mark the bit as seen. Okay, and just as for majority, I can say it's A. Right? So what does this mean? Somehow, let's say I start with state Q0, or let's say Q start. All right? I read a 0, somehow I should, and if I see a 0, then you say, okay, jump to Q saw 0. Okay, so I saw a 0, so I'm just going to jump to a state which is called I saw a 0, so you have to go look for a 0 next. Okay, I'm going to replace this one with a marked symbol, so I'll call it an A, right? And then I'm going to move one step to the right. Okay, so that's my transition function. I see a state, and I'm at the start state. I see 0. I say, okay, you saw 0. Mark this 0 as seen. This would become an A, and my head move to the right. Okay. And then the suggestion was, okay, you scan to the end of the tape. Right? So palindrome means that the first and last symbols match, the second and last but one symbol match, and so on. Right? So I have to scan to the end of the tape. How can I recognize that I've seen the end of the tape? Again, remember, we are very local. I can only see what's basically hitting me in the face or written right below me, right? So how do I know I've reached the end of the tape? Yeah? Right. So once I see an empty cell, I know I've reached the end of the tape. I just had to backtrack one step. Okay? Scan to the end of the tape till you see a empty symbol. Move one step left. Okay? Because you reach the end, so you come back one step left, and then check if the symbol matches what was remembered. Okay. You have to be a little bit careful about one border case. Like when you back up, maybe you're reading the same symbol, which you might have overwritten, but that's okay. As I said, don't worry about the edge cases too much. As long as we are focusing on the main idea for now, the edge cases, you can code them up too. Okay. Check if the symbol matches what was remembered. If it doesn't match, what should you do? If the first and last symbols match, you know the answer to the function, right? It's not a palindrome, so you don't have to redo everything. You can just, the answer, okay? So you say, you enter a state which is going to say clean up the tape and return 0. Okay? If yes, what should you do? Any suggestions? If yes, what should you do? Yeah? When you're at empty. Exactly. I think that's important because remember, once I see this, this 0 and this 0 match, next time I shouldn't go this far, right? So again, there are various ways, but that might be one of the best ways to do it. So mark this symbol as phi, and then you basically repeat, go to the first unseen symbol next. Okay? And how do you know you reached the first unseen symbol? How do you recognize that? So meaning, okay, so let's say at some point this has become A, this has been erased, this has been marked as A, this has been erased, and you are here. Now the instruction says go back to the first unseen symbol. How do you know you reached the first unseen symbol? Yeah? Exactly. Keep going left until you see a A. Once you see a A, take one step to the right. Right? So it seems so cumbersome, right? You can only see one step at a time. So it limits what you can do, but we're able to kind of, bandage over all these limitations and do stuff still, right? I can't really scan the entire thing and say, okay, find the first A, so last A or something like that. So you keep scanning from right to left until you see A. Okay. right? And then if you never return 0, then you basically, if no more unseen bits, then cleanup tape and output 1. Okay. So, if you're thinking about designing a Turing machine, the expectation from me is you'll be able to think in this way, right? You don't have to show me or think about how to write down these detailed instructions, okay? But really, there's a difference in how you compute things with a very local view. And that is captured by instructions like this: scan to the left, scan to the right until you see something, and so on, right? As long as your instructions only depend on what the head is seeing, it is fine. You can't just say count the number of ones, count the number of zeros, and so on. Okay, any questions? All right. And the best way to access this again is this way. Oops. What happened here? All right. So what I'm going to do is you'll have a link to this server. This is kindly, maintained by another, someone who really cares about Turing machines. And there are some. If you access it, I'll send you the ID and password. There's also a class version where you can add new machines if you want. I've had some people do that in the past. But like if I say in-class palindrome, then you'll be able to see the code. Okay. Let me say a few words about this. For example, here, this segment is saying, remember first unmatched symbol, right? If you see a 0, you know I see a 0. If I'm in starting state and then see a 0, you say, okay, go to the end and match with a 0, right? And so on and so forth. Okay. So let's say I have this as my input, load. Okay, this is not using A, it is using just making it empty, but that's fine. That also works. All right. Let's say I put one extra 0 here and increase it. All right. So, it seems a terrible algorithm because it's making multiple passes again and again and again. But, as I said, as far as primitive models go, it's what we are doing right now. Okay. All right. So one takeaway for you should be that, TMs are really a simple computational model. Okay. By simple, I mean it's very easy to describe the entire computational model, right? You just have a transition table and that's it. Okay. If I have to define like a new programming language, usually it's much, much harder. I have to tell you, what the different variables mean, what is the syntax, everything like that. Turing machines, it's very simple. To code it up, you just have to define the transition table, and after that, it's just lookups one after the other. Okay? And we can really think of it as a new programming language. Maybe for most of you, this won't be your first choice programming language. But if I force you, you could potentially try and solve problems in this programming languages. Okay? I'm calling it a programming language because I can write down a series of instructions to be followed on any input, and then you'll have some output. Okay? So at this point, we have defined a computational model. We also have a new programming language, however rudimentary it is. All right? Okay? Now, obviously, it seems really silly programming language. Let's compare to something like Python. Okay? It has many, many features in it. So for example, what are some really nice features in Python that you like? Yeah? Nobody likes Python these days? Okay, I'll tell you one of my first things is variables. Okay, I can create new variable names and so on. In Turing programming language, TM's there's no notion of a variable. You can say maybe a state, but you can only create a few of them. Okay, it has to be finite, right? What else? What are some of the things we take for granted in a Python program? Sorry? Well, okay, libraries are there, but even think, let's say, first principles. I'm not even going to call libraries as much. We'll talk about that, but even some simple, like inbuilt functionalities. Yeah? Lists, right? And one other thing, I think this is one of the things that seems so important when you think of a programming language is random access. Imagine writing programs where you have to deal with arrays, but you cannot index. You can only go one step at a time. Right? It's not just that you can go one step at a time, but you can't even remember how many steps you need to go. Okay? But in Python, I can say, okay, if x100 equals x1, do something. Right? What else? Yeah? Loops. Yeah? I can write for loops. What else? Yeah? Yeah, ability to call functions. In particular, recursion. Imagine computing various things without recursion. That'd be so tedious. Right? Or even more basic, like if-else conditioning. What else? I can also update many things in one go. And we don't even think about updating many things. I can say, okay, this entire array equals this entire array. Whereas in a Turing machine, you can update one cell at a time. Right? Okay? And this is just for Python. You can take any other programming language, at least they will have all of these basic features, right? And obviously, our primitive, ultra primitive Turing machines don't have any of these. Okay? Nevertheless, Turing machines can implement all of these. Like for example, you can do random access. You can simulate random access by only having this single steps at a time. Okay. We won't cover this in detail, but you'll see it in homework, kind of build the pieces for it in the homework. And the code for it is also available in the simulator if you want to play with it. Right? You can simulate all of these functionalities. For example, as I said, it can do random access. Okay. And this is for Python. What other programming languages do you guys use? I definitely learned C and C++ before I saw Python. What else? What are some other programming languages that you like? JavaScript, okay. What else? If you wrote JavaScript, let's also write Java. Nobody likes strange programming languages here? Okay, I'll write one. Haskell is definitely very strange. Have you ever programmed in Lisp? I see a few people nodding heads very enthusiastically. What else? Yeah? Pro, okay. Prolog, Fortran, and so on. Okay? So each of these languages, they have so much. For example, if I tell you, okay, specify Python to me, that's like, it's a huge document that you have to tell me what it means for a Python program. And the specification is humongous. It comes with its advantages. Now that we have the specification, we have all these libraries and so on that we can use freely, right? But the description complexity of all of these programming languages is humongous. Okay? And whereas Turing machine programming language, I just told you, it's just that one definition. You have to tell me what a table is, and that's it. Okay? But it turns out that Turing machines can do Python, can do C, C++, can do JavaScript, can do Java, can do Haskell, can do Lisp, can do Prolog, can do everything. Okay? And we will, this is one of the most surprising theorems that we will state without any proof. Okay? And it's the following. For every Python program, P, there exists a Turing machine M such that for every x, the output of P of x is exactly the same as. Give me any Python program, there is an equivalent Turing machine which does the same exact computation. All right? And not only that, if you think of majority, okay, if I ask you to solve majority on Python, how much time would you need? Any guesses? How much time would computing majority of x take in Python? If it's n, I have to scan every bit, so n. Right? I make one pass over the array, I add up the ones, and I know the answer. Right? Whereas the Turing machine that we wrote down, how many steps is it taking? Okay, so majority x Python versus Turing machine. How about Turing machine? How much time does it take? The one that we wrote down. Well, you had to make you read a bit, you have to go all the way potentially and then come back. You read another bit, you go all the way into the end potentially and come back and so on, right? You might be doing a pass to the entire input every time you see a 1 or a 0, right? So it roughly takes t squared or t squared iterations or t squared transitions. Okay, meaning the cost of the Turing machine for majority is roughly quadratic, right? For Python, I could have just made a single pass. My rudimentary Turing machine, it said once you find a 0, okay, go look for a 1. So that might force you to make an entire pass over the input. Okay, and then you find another 0, you had to make another pass to find the next one and so on. Okay, so it's quadratic. Okay, and the bizarre thing is this is some of the worst possible conversion. Not only can every Python programs be simulated by a Turing machine, you can do this with at most a quadratic overhead. Okay, right? So in some sense, we have this single, very simple model, which is just as powerful as any programming language, and not just powerful in terms of what it can compute, but also, relatively fast. It is slower, but given its simplicity, the fact that it's only quadratical is slower should be surprising. Okay. Any questions about the statement? As I said, this is kind of a very important theorem that we are not going to prove, but it is important. Right? So in some sense, we already had a perfect model in Turing introduced Turing machines. As I said, he didn't call it that in 1936. Okay, before NFS and so on, even before kind of regex was well studied, Turing machines were already defined. Okay. All right, so let me say a few things. First, Turing is a really remarkable figure. He invented Turing machines, and he also did many other things. He was also a long distance runner, and he headed very important efforts during World War II on code breaking, right? And he kind of headed a lab which had the first computing section where humans would mimic computing to break codes during World War II. Okay. He was responsible for designing the Enigma machine. There's a movie about it. So this was a very important technological help for the war efforts in World War II in breaking code messages and so on. So they had to build a machine which can do that, right? And you can see if you read about the history, it's not exactly a Turing machine because it has to be transportable, implemented, and so on. But there are some similar ideas being used there. And in this context of designing this machine and code breaking, kind of also did really important work in statistics. Later on, he did really good important work in evolution. Kind of also talked about Turing tests for AI and many, many other things. Okay. And so for example, this is some rendering of a Turing machine. You can see there's one infinite loop where you're writing. The funniest Turing machine joke that I've seen is this one. I've never, 1 year when I taught this class and I showed this, the next class, one of the students came back with a candy button paper for me to eat. So don't do that, please. But you can even, this is exactly what a Turing machine is doing. You really have an infinite candy button paper, right? And you're just chomping one at a time. You don't eat randomly. You can chomp one, scroll left, scroll right, and that's it. Okay. All right. And yeah, so to me at least, just this definition and the contributions, as we will see, should kind of put the influence of this idea of machines and computing as formalizable goes all the way back here. And I would say this is clearly true. Okay, and you'll see why. Maybe a little bit more this lecture, definitely the next lecture. Okay. All right. So let me stop philosophizing and talk about science, right? Now, I told you that Turing machine can simulate any other programming language, right? And with not too much of an overhead. Now, the question is, can we make something more powerful? Right? So if I ask you to design a definition, okay, so Turing machines were a simple extension of DFAs, right? I added read write, I added the ability to go left and right, okay? But imagine you were coming up with this definition, would you stop there? Do you think this is kind of the pinnacle of computing power, or other things or are there other things you can do? Okay. So let's say I ask you to define more powerful Turing machines. What are some things you would try? Any guesses? Yeah. Yeah, one of the things that we exploit a lot in modern architectures and programming and so on is kind of parallelism, right? In a Turing machines, it's also very easy to have. I can have multiple tapes. Okay. So meaning, what does multiple tapes mean? I can imagine, let me do a 2-tape version. There are 2 tapes. Basically, instead of having 1 array, you have 2 arrays. That's it, right? And here, on the first array, you have the input loaded. Okay. And the other array, you just have empty to begin with. Okay. And you can come up with all kinds of variants. So let's say I have 2 heads and they can move independently. Okay, remember, I'm defining a new computational model. So in some sense, I have to be very specific, right? I have to tell you what are the ingredients into it, how does it function, how would you describe it, and so on, right? So I have 2 heads. Okay. So, a 2-tape Turing machine now would be described by a transition function. I can have certain number of states. Again, you can have a separate state for the first head, separate state for the second head. Let's say you have a single state. Okay. And takes 2 symbols as input now. Right? My state can see this bit and wherever the other head is showing. What should the output be? Like a DFA, you would jump to a new state. Okay. And what else? I have to specify if I'm rewriting this symbol. I have to say what I'm doing for the second head. Okay. And lastly, I have to tell you what happens for the first head and what happens for the second head. Okay, very natural extension. So instead of having a single tape, now I have two tapes where my transition function reads both symbols. And I have two legs, one running on one tape, the other running on the other tape. I see both my symbols and then decide to do something. I jump to a new state. I decide to rewrite on the first tape, and decide to rewrite something on the second tape, move my heads left or right, either way. Okay. And then, let's say the output is whatever is written on the first tape. Okay, that's my definition of a two-tape Turing machine. All new computational model. Okay. But nevertheless, it turns out that two-tape Turing machines can be simulated by a one-tape Turing machine or just a Turing machine. Okay. How to do this? It is tricky. I define a new computational model, but I'm saying it has the same power as the old computational model. It's a little bit like what we did for DFS and NFS. We defined a seemingly more powerful model, NFS, but it turned out that they had the same computing power as DFS. Now I have two tape Turing machines. It turns out they have the same power as one tape Turing machines. Okay. And one thing I will say though is if you go back to this theorem, and we won't give a proof of this too. It turns out there is a two-tape Turing machine M also, no surprise. Okay, a single-tape Turing machine is also a two-tape Turing machine. But if you allow me two tapes, then my simulation becomes t times log t. Okay, so I can simulate any Python program by a two-tape Turing machine where the overhead in time is only logarithmic. Okay, this is startling, right? Because you have a very sophisticated language, but if you unravel it, the amount of time Python would take is roughly the same, roughly up to this log factor on a two-tape Turing machine. Okay. All right, so multiple tapes, same power. What else? Think of other ways of powering up the model. Any suggestions? Well, you allowed multiple tapes. Why don't I allow multiple heads on the same tape? Again, it turns out this is equivalent, can be simulated. By Turing machines. Okay? And in general, Turing machines are, the definition is surprisingly robust. You might think I will have two tapes, 10 tapes. They are all essentially equivalent to a single tape Turing machine. Okay? And not only that, they're also very, very powerful. Okay? And this is kind of codified in this far-reaching hypothesis that was made by Church and Turing. Church was Turing's thesis advisor when Turing was a PhD student in Princeton. And kind of this is what they came up with. Every function is computable. Okay. So saying every function that is computable by physical means is computable by a Turing machine. Now this is very vague, okay? And reason it's vague is that it is really not a theorem or a hypothesis. This we are claiming is a new law of nature. It's a limitation in our physical world. It's saying anything that is realizable as a computational model in given our current laws of physics can actually be computed just by a Turing machine. Okay, and everything that people have dreamed up with, like quantum computing, you can think of relativistic computing and all of those other things. Every one of them, it turns out, can actually be captured by a Turing machine as well. So no one has come up with a plausible physical reality where you get a model which is not computable by a Turing machine. So in some sense, this very rudimentary programming language is just as powerful as you can ever get. Okay? Yeah? By what? Like basically by physical means is just saying that by our laws of physics. Okay? You might come up with a crazy theory where your hypothesis is that Turing machines are not powerful. Okay? But consistent with our laws, it seems like Turing machines are the most powerful computational model. Okay? It's a vague thing, it's a law of nature, right? It's saying you cannot do anything that is not computable by a Turing machine. Yeah? It's just a statement. Yeah. Potentially, but again, the belief is that our current laws of physics don't allow it. Okay? It's like physics, right? You can't really prove a theory. You can only get a counterexample. In the same way, until you find a counterexample, every experiment we've done for this, theoretical or practical, has resulted in verifying this law. Okay? When I think of quantum computing, again, they are simulatable by a Turing machine. At a greater cost, but nevertheless, you can still do it. Okay? And this leads us to what I'm going to call a principle, which is HOCAEIT. Okay? What does, uh, okay. Any guesses for what the acronym stands for? Have our what? Cake and eat it too. Okay, so what does this mean? So kind of the have our cake part is to show something is computable. Okay. Suppose I tell you, okay, is there a Turing machine which can multiply numbers? You might think, that's how do I write it down? I need to write down a transition table. Remember, multiplication is a fixed function, right? The function is universally specified. It can work on arbitrary length inputs. So writing down a Turing machine for that is saying, give me a machine which has, maybe 10 states, alphabet size 4, and that's it, right? So the description length is maybe 100 transitions, 1,000 transitions at worst, right? I just have this one table that can multiply numbers, any numbers. It's not like I'm learning multiplication tables. I have this one transition table which tells me how to multiply any two numbers, no matter how long they are, right? That's kind of how algorithms work. It's a single answer to many, many, many questions. And here, the answer is even just one transition table. That's it. That's what an algorithm is. Okay. To show something is computable by Turing machine, we can use a high-level programming language. Okay. So meaning, if you ask me to write down multiplication, tell me there is a Turing machine for multiplication, I'm going to first write down a Python program and say, use my all-powerful conversion theorem. This theorem applies for any program. So in particular, it applies for multiplication. Okay, so it makes designing Turing machines very easy, or at least we can take it for granted. If you can write a program, I can convert it to a Turing machine, right? And you might think this is like a dumb idea. Why would you ever want to convert a programming like a Python program into a Turing machine? Well, there are some very good applications for such conversions in cryptography and verifying programs, and nowadays even in cryptography as well as in the crypto world, where you're doing proofs of work in Bitcoin and so on, people routinely convert programs into much simpler models like Turing machines and then work with the Turing machine. Okay? So it's not just an operation that you can do in theory, it is routinely done in practice as well. And given Church-Turing thesis, we are going to be a little bit grand and just say a function is computable. Earlier, we were saying computable by circuits, computable by Boolean circuits, computable by NAND circuits, computable by DFS, NFS, and so on. Now we're just going to drop the qualifier and say it is computable if there exists a Turing machine M such that for all x, f of x equals m of x. Okay, function is computable if there is a Turing machine which can compute it. All right. Okay. Now that's the have our cake part. What is the eat it to part? Any guesses? No. So think of it this way, right? In some sense, Turing machines are so simple that it's much easier to reason about them. Okay, in the following way. If I want to show that something is not computable, it would be much easier potentially to say, okay, Turing machines cannot do it, right? Whereas to show that Python cannot do it might be more cumbersome. Okay, but both are equivalent because of our theorem, right? So the ET2 part says to show something is uncomputable. We just have to show Turing machines cannot do it. Okay. So have or cake means, to show something is computable, I can use any powerful programming language that I want. Whereas if I want to show it is not computable, I just have to rule out Turing machines. And the heavy lifting will be done in either case by this theorem, that every Python program has an equivalent Turing machine with roughly the same cost. Okay. Any questions? Yeah? Right, but that's easier to show. You're absolutely right that we need to do that, but we can do that much more easily. Like given a Turing machine, I can do arrays, right? So it's very easy to do the other way. Okay. So in some sense, every programming language should really start with Turing machine instead of assembly level or anything like that. It's the simplest possible programming language, and nevertheless is just as powerful as anything else you can find. Okay. And hold on, I might have one. Oh, I don't have a picture of that, but okay. So all of this was done by Turing in 1936. He defined the machine, and he also showed a couple of other things that we'll talk about after the break. Okay, let's take a short break, and when we come back, we'll talk about more properties. Okay, so what did we do so far, right? So, for the nth time, we defined a new computational model. But we don't have to go through a series and series of models anymore. This is all that we need. So it is very powerful. And can simulate other existing models. Okay. So this is already a significant development, but Turing did not stop there. In the paper which introduced this, it's called, this is the paper from 1936, 12th November, on computable numbers with an application to the N-Scheidung's problem. Someone with better German pronunciation should do it. But anyway, so this is a problem in logic that Turing was trying to solve. It's connected to Gödel's incompleteness theorem. And in the course of solving that question in logic, he defined Turing machines and did a couple of other things which are really, really important. Okay? And that's what we're going to focus on for the next couple of lectures. The first one is what is called universal Turing machines. Similar in spirit to the idea of universal circuits we saw way back in the early ages of computing, right? So we defined circuits and we said, okay, in fact, if you really care about it, you don't have to keep on designing or rewiring for every new circuit, right? You just build one circuit, connect these wires in this specific way, and then simulating any other circuit just amounts to toggling some input bits. Okay? It's something similar, but even more powerful in the following way. There is a single Turing machine that can simulate all Turing machines. And we'll call this a universal Turing machine. Okay? And this is very different, even though similar in spirit, it's way more powerful than the circuit definition, as we will see later on. Okay? So it's saying not only can Turing machine simulate any programming language, in fact, there is a single Turing machine. You can write it down in like one, the simplest possible one. Maybe you can write it down in 10 pages or 5 pages. Just 5 pages of transition table, and that defines a computer now. And that computer is as powerful as any other computer you can build. Okay, that's the far-reaching conclusion of this statement. We'll make it precise. As I said, even just understanding the statement takes some work. The other thing that Turing also did, in fact, in the same paper, is uncomputability. Okay. So take the example of DFAs, right? We saw majority cannot be computed by a DFA. No matter how big a DFA you pick, it cannot be computed by a DFA, by an NFA, by a regex. But it can be computed by a Turing machine, right? And it turns out Turing machines are unfortunately not all powerful. They're as powerful as we can be, but they are not all powerful. There are functions that are uncomputable. Technically, that are uncomputable by Turing machines. But as we said, computability by Turing machines is all there is. So just saying that there are functions that no computer can solve. Okay, there is no algorithm for computing these functions. Okay, so these are kind of two of the greatest hits, really, and they're all in this paper. So this paper defined what a Turing machine is, showed universal Turing machine, and also showed that there are uncomputable things. Okay, so in some sense, if you're an ML person, I don't know if you know this joke enough, but if you're in machine learning, you would call this paper Turing machines is all you need. Okay, there's a famous paper called Attention is All You Need. This is a pun on that. Okay. Thankfully, Turing was more grounded. All right. So to do this, we had to first talk about universality. Okay. And kind of our trajectory for that will be very similar to what we did for circuits. Yeah. No, right? This is just saying that there are functions that are uncomputable by Turing machines. Okay? Church-Turing thesis is a relative statement. It's saying if there is a machine or there is under some physical process that can compute it, then a Turing machine can do it. Okay, it's all a relative statement. It's basically like saying, there are problems that if any one of you can solve it, then someone else can solve it. But it doesn't say anything about problems that no one can solve. Okay, it's a relative statement. Church-Turing thesis is a relative statement, whereas this is a theorem. That's a thesis, right? That's a law of nature. We cannot prove it no more than we can prove gravity, right? You can keep demonstrating it forever, but that's not a proof. Whereas this one, uncomputability, is provable. Okay, yeah? We'll talk about that, yeah. In fact, there are very simple functions, simple to describe, and functions which we really, really, really care about that turn out to unfortunately be uncomputable. Okay? All right, but we have to get there. We have to formalize what it means to do these things. Okay? And our trajectory for this is going to be similar. So it kind of starts from the same principle as for circuits. It is code as data. Okay. We'll see how Turing machines, so far I've been taking strings as input and outputting something. We'll start viewing those inputs themselves as Turing machines. Okay. And then this will lead us, just as for the circuit's case, to the two conclusions. Right? So universality and uncomputability. Okay. All right. So let me talk about this code as data. And it's been a while since we talked about representing things as binary strings. And we've done it a zillion times so far. So for this time, I'm just going to wave my hands vigorously and only sketch kind of the outline of the encoding. Okay, we're not going to be in the weeds again. Okay. So let's think of what it means to describe a Turing machine. Right? So someone else is in another room, and you want to shout out what or describe the Turing machine to that person. What would you need? What would you really need? Well, it's completely described by the transition table. Right? And so the number of states is k, and the number of alphabet symbols equals L. Okay. I might just be using 0, 1, our triangle, empty, and then maybe some other things. Okay. And how would you write it down? As I said, to describe the computer, you just had to write down a table. Right? So state, symbol, new state, new symbol, action. Action refers to what you're doing with the head. Okay? So you have to write this down. So, on state 0, on symbol 1, you go to state 19, you rewrite it with symbol 0, and then move to the right. Okay, so let's say sigma is 0, 1 through L minus 1. All right. So the alphabet doesn't really matter what you use there. As long as you have 0, 1 in it, it should be fine. And the others are kind of placeholders. They're like variable names. Okay. So delta I comma A is J comma B comma some action. New state, symbol, action. All right. So you're in one room, the other person is in another room. We have to convey this table to that person. How would you do it? Well, I'm just going to shout out 5 numbers at a time. I'll say 0, 1, 19, 0, R, 0, 0, 17, 0, R, something like that. Okay, I can keep shouting these things. You write it down, then you can reconstruct the Turing machine. Right? So I want to represent the Turing machine as a string in 0, 1 star. Okay, and I can do this because the Turing machine is specified by the transition table, and I can think of the transition table as a list of 5 number tuples. Okay, so basically, the state will have a number, the symbol will have a number. So let's say sigma is again 0, 1 through L minus 1. As I said, this is kind of almost by convention. And for the actions, also let me introduce some code so that everything is a number. So let's say left is 0, right is 1, stay is 2, halt is 3. Okay, so now, for instance, if I say something like 0 is 37 10 R, this will be translated into 17 0 37 10 and 1. Okay, it might not be the most efficient way, but we don't care so much about efficiency, right? But a Turing machine is just a list of 5 tuples of numbers. Okay, and how many such tuples would I need? Like, how many rows would I have here? Right? For each state and each possible input, I have to tell you what you would do. Right? Just as for a DFA or for every possible input and for every possible state, for every possible state and every possible bit, you have to tell me what you're going to do. Okay? So I would have roughly k times L many rows. Right? So what does this mean? Turing machine is equivalent as a list of 5 tuples of integers. Okay, so imagine this is your programming language. You just blurt out 5 tuples of integers, and that's a program for you. Okay, but that's what a Turing machine is, right? So if you have a Turing machine, it takes some states, some alphabet, which we kind of identified with that. This is sigma. I can specify it by saying, maybe I'll tell you the number of states up front. I'll shout out the number of alphabet symbols, and then I'll start writing down 5 tuples. Right? So first tuple, and then the next 5, and the next 5, and so on. Okay? So how many tuples would I have? I would have k times L many 5 tuples. Okay? We don't need the length of the encoding, but let's just figure it out anyway. So to encode a Turing machine with k states and L symbols is equivalent to a list of 5 times k times L plus 2 many integers. right? I mean, there's some redundancy. I'm telling you these two things just for clarity, right? If you have 10 states and 4 symbols, then you say 10 comma 4, and then you would write down 40 times 5, 200 many numbers. So that would be the complete description of the machine. Okay, so 202 numbers would be a machine that can actually compute, for example, majority. Okay, right? And once I have a list of integers, we can map it to binary strings. We've done that many times. So how would I encode Turing machines? First, encode Turing machine as a list of integers as above, and then use okay. We know how to do this. We can get a prefix-free encoding of integers, concatenate all of them, and that would do it. All right, so we've done this many times. So what is the summary here? The punchline is the following. We can map, let's call it encoding TM for Turing machine, not for trademark, which maps any Turing machine to a binary string. Okay, and it's a reasonably efficient encoding too, right? So if M has K states, L symbols in the alphabet, then the encoding of M has length roughly okay. So K times L, because that's how many integers you have, up to constant factor, and log K plus log L, because each number takes some number of bits. Okay, this is just some bookkeeping, not important for us, but just to say that we can represent Turing machines as binary strings very succinctly. Even the numbers fact is kind of bizarre, right? So if I tell you a list of 202 numbers, you can go and compute with it. Okay? So your programming language is now just blurting out number sequences. All right. And so one way to think about this is the following. You have all possible Turing machines. So that's supposed to be a laptop, by the way. Looks like an arrow if I think it was. Yeah, maybe this is better. All right, so you have a bunch of Turing machines, all possible Turing machines, and we have binary strings. Okay, and encoding maps each one to a unique string here. Maybe this goes here, this goes here, this goes here, and so on. Okay, so proper encoding, so every machine gets mapped to a different string. And since we'll be dealing with these encodings a lot, let me introduce some notation for it. So any Turing machine M, we denote its encoding as this angle braces around M denotes the binary string which denotes its encoding. Okay. So when we start working with encoding, writing encoding of M every time becomes cumbersome. So just this parenthesis means that I'm looking at the encoding of the machine as a binary string. You have a machine, I convert it into a binary string. These angle parentheses are referring to the sequence of bits which describe the machine completely. All right. And you can think of it as, qualitatively, M is the machine, this is the source code. Okay. Any questions about this? All right. And lastly, there could be strings in 0, 1 star that are not valid encodings. Okay, there could be strings in here which never occur as valid encodings. For example, every Python program, you can convert it to a binary string, but not every binary string would correspond to a Python program. They need to have a very specific syntax and so on. Okay, but again, to simplify notation, because otherwise you have to say if it is a valid encoding, do something. If it's not valid encoding, ignore it, and so on. We are going to adopt a convention. If a string alpha is not a valid encoding, of a Turing machine, just set it to mean a Turing machine that always outputs 0. Can just adopting a convention that if something is not a valid encoding, in Python, for example, if you have a combat program, it'll say compilation error. Here I'm just saying, okay, adopt the convention that it defaults referring to a Turing machine which always outputs 0. It's not doing anything. Okay? Any question about this? So now every binary string corresponds to a Turing machine, and every Turing machine corresponds to a binary string. All right? Okay. So we can define a function now, which is eval okay. So it's a little bit trickier to define eval here compared to for circuits. There's one important subtlety. I'll talk about that in a second. Right? So eval takes as input the description of a machine and an input, again in binary, for that machine, and is supposed to mimic the behavior of M on X. Okay? And what does mimic mean? If the machine on input X terminates with an output, then your simulator or eval function should terminate with that exact output. If your machine on that input goes into an infinite loop, then your eval should also go into an infinite loop. Okay, if it's not halting, then you're also not halting. Okay, this is really, the analog of a simulator or executor, like compiler plus interpreter, etc. Okay, so we are saying eval just takes the description of a machine and a potential input and mimics the behavior of the machine on that input. It's really an executor, right? So you're executing a program. So when I call GCC C program and input, this is exactly what it's doing. You give a program as input and input for that program, and the simulator runs the program and tells you the answer. If it actually gets an answer, otherwise it also does the same thing, right? And this perpendicular here, remember, was our notation for saying we didn't get an output. It's not that the output is perp, but the notation is saying that we didn't get an output. Yeah?
That's if it goes in perp.
Yeah. Again, the perp is not like I'm outputting the symbol perp, it's just saying that I didn't get any output. It's like a code dump error. I ran into infinite loop. That's where I am. Okay? Any questions? All right. So now we can view programs as input. That's what we are doing. And this is one of the most bizarre things that we can do in computing, which is to eat ourselves in the following sense. A program taking another program as input is also possible now. If you think of a C compiler, it's a program, but its input is typically another program. Okay? In the same way, we can think of eval as a function which is taking other Turing machines as input, right? Now I can ask, what would be a natural question next? Eval is a function, it's well defined. Yeah?
So,
Yeah, is eval computable? Okay. When we asked the same question for circuits, it was an easy answer because circuits could compute everything, right? But it's not clear the same is true for Turing machines, right? We don't know they can compute everything. In fact, I claim there are functions that you cannot compute. Maybe eval is one of them, who knows, right? But luckily for us, eval is computable by a Turing machine. And who showed this but Turing in 1936. Okay, so he showed that there exists a Turing machine U such that U of m comma x is eval of m comma x for all m comma x. Okay, this is highly circular. This should be very bizarre. It's saying there exists a Turing machine that can compile plus execute Turing machines. It almost feels like we're eating our own tail, right? So this is called really meta-circular evaluators. Okay, like for example, you might have heard it said that GCC is written in C. That makes no sense, right? If you think about it, if GCC is written in C, who is compiling GCC then? It's kind of a lie when people say that. But what you do is you build a core of a language in assembly, and then use that to write new things and so on. Okay, but the core is like a universal machine, right? It can simulate any other Turing machine. Okay, and it's a very important idea, and this is actually what makes a general purpose computer possible. Okay, so you should really think of designing a computer as you build a universal Turing machine, and then it can simulate any other machine that you want. Okay, and we'll talk about more implications in the next lecture. But let me end by saying now we know there are universal Turing machines with 25 states and alphabet 0, 1, this. You have to be very, it's not at all clear why eval is computable. Think about it. A Turing machine only does things very locally. Now, I have the transition table written in binary sitting on my tape and the input X written somewhere else, and I have to somehow mimic that Turing machine on my tape. It sounds impossible. Okay, but it is possible. In fact, it is possible with only 25 states and 4 symbols. Okay, so in some sense, if you are asked to forget all of computing but only remember 100 numbers, these should be the 100 numbers. 100 times 5, right? So a sequence of 502 numbers. A sequence of 502 numbers is a universal machine. It can simulate any other program. It can run any other program. Okay, so that's one really surprising implication. Okay, we'll kind of see a sketch of the proof of universality by cheating, of course, a little bit by having our cake, to be honest. But that's okay. The main takeaway should be this conceptual leap that happened. We don't have to design machines every time. A single machine can simulate any other machine. And it's even more bizarre here compared to circuits, because in circuits, we're designing a universal circuit could only simulate circuits up to a certain size. Okay, but there's no such limitation here. This Turing machine with 25 states and 4 alphabet symbols can simulate a Turing machine which has 1 million states. It can simulate whole of Python if you want. Okay, so this 502 numbers is just as powerful as a Python interpreter. You give a suitable encoding of the program, and it'll tell you the answer. Okay, we'll talk about this and other implications in the next lecture. All right, so I'll see you on Monday